All right, in this video, we'll discuss section 2.3 dealing with other set operations. And in this section, we'll recognize relations between set operations and logic connectives, and also construct Venn diagrams and use them to sort and reason with data. All right, so there are two things we'll look at. First, set intersection and set union. Okay. Now let's talk about first set intersection. All right, let's say we want to consider the following sets. C is considered to be the set of all X such that X is a college graduate, and S is going to be the set of all X such that X earns at least $40,000. And suppose we want to mail a questionnaire to all individuals in a certain city who are college graduates and who earn at least $40,000. Then the individuals to receive the questionnaire include those common to both sets C and S. So if you look at this Venn diagram here, you'll see what this means, the intersection. And the shaded area is going to be the intersection of set C and S. Here, this means that the individuals that are to receive the questionnaire will include those that are common to both set C and S, those who are a college graduate and who earn at least $40,000. Now, this leads us to the definition of set intersection, which is this. The intersection of two sets, A and B, is written like this. And we call that, or we can say this is A intersect B. That is the set of all elements common to both A and B. Now, if we look at it in set builder notation, it will be this. The intersection of A and B will be the set of all X such that X is an element of A and X is an element of B. And the key word in this case is the word and. That implies that both conditions must be met. So let's look at a few examples of this. Finding the intersection of A and B in each of the following. Like in part A has the elements 1, 2, 3, 4. B has the elements 3, 4, 5, and 6. So to find the intersection of A and B, we need to find or identify the elements that are in both A and B. They have to be in both A and B. In this case, notice that the number 3 and the number 4 are in both A and B. So the intersection of A and B will have to be the elements 3 and 4. We don't include the 1 because 1 is not included in B, and neither 2 will be included because it's not in B. 5 and 6 are not included because both of those numbers are not in A. Only the 3 and the 4 are in both A and B. That's how we find the intersection of the two. Now, part B, we got A with the elements 0, 2, 4, 6, and so on. B, an infinite set with the elements 1, 3, 5, 7, and so on. So we need to find out what elements are common in both A and B. And in this case, there are no elements that are common in set A and in set B. So here, the intersection of A and B is the empty set. And another way to think of this is that A and B are what is called disjoint sets, meaning what's in A is not in B and what's in B is not in A. Okay, excuse me. Now part C, we got A with the elements 2, 4, 6, 8, and B with the elements 1, 2, 3, 4. And here I want to find the intersection of those two. So we want to find out what elements are in both A and B. Well, notice A is the elements in A are also in B if we were to expand this out a bit. So if we take the intersection of A and B, it's going to end up being set A because all that's in A is also in B. So that's how we find the intersection of two sets. Okay. All right, next we'll look at the union of two sets, or set union. All right, now let's consider these two sets. Again, C is the set of all X such that X is a college graduate, and S is the set of all X such that X earns at least $40,000. And let's suppose we want to mail a questionnaire to all individuals in a certain city who are college graduates or who earn at least $40,000 or both. Then the individuals to receive the questionnaire include those who are members of set C or set S. So if we look at the Venn diagram that you see here, this represents the union of set C and S. So we're including all elements that are, common, that either is a college graduate or earn at least $40,000. And we're including both those who are college graduates and earn at least $40,000. So that would be the union of set C and S. All right, now on the next page, you'll see the definition of set union, or the union of two sets, A and B. And it's going to be written like this: A union B. That is going to be the set of all elements in A or in B. Now, the word or is going to be that key word. And it's going to be very important because the word or is being used as the inclusive or. We call that the inclusive or. And of course, A union B is going to be the set of all X values such that X is an element of A or X is an element of B. Now the or implies one or the other or both. And that's what we mean by inclusive or. Either in set A or set B, or it could be both A and B. So now let's look at a few examples of this. Here I want to find the union of A and B. That means I'm going to join the two together. That's what union means, by the way. Let's say in part A, set A has the elements 1, 2, 3, 4. Set B has the elements 3, 4, 5, 6. And I want to find the union of the two. So that means I'll list all the elements that are in A or in B or in both A and B. And I list each element only once. So in this case, A union B, written like this, would be this: 1, 2, 3, 4, 5, and 6. That's A union B. And notice I only list the 3 and the 4 only once. Part B, let's say I have A with the elements 0, 2, 4, 6, and so on, and B with the elements 1, 3, 5, 7, and so on. So if I find the union of A and B, I just put those two together in numerical order and only once. So in this case, this will be 1. Actually, it starts with 0, I'm sorry. Didn't see that. There's 0 right there. Let's start with 0. And then 1, 2, 3, 4, 5, 6, 7, and so on, since they're both infinite sets. And in part C, we got A with the elements 2, 4, 6, 8, and B with the elements 1, 2, 3, 4. Okay, and I'm going to find the union of A and B. So here I'm going to put those two together and list each element only once. So here, this starts with 1, and then 2, 3, 4, and so on. And this, and you know, those 3 dots will include the 6 and the 8, by the way. But notice here, this is the same as set B. Okay, and since every element of A is in B, we can say here that the union of A and B will end up being set B. Okay. So that's how we find the intersection and the union of two sets. Now let's talk about set difference. So we want to consider the two sets here, the same two sets that we talked about, where C is the set of all X such that X is a college graduate, and S is the set of all X such that X is someone who earns at least $40,000. So here the set of individuals earning at least $40,000, but not a college graduate, is called the complement of C relative to S, or the set difference between S and C. Because someone can earn $40,000 and not be a college graduate. Okay. So on the next page, you'll see the definition of a relative complement. The complement of A relative to B, written like this. Now, keep in mind, we have to say the complement of A relative to B. It may look like B minus A, but it's not actually B minus A. That's the set of all elements in B that are not in A. So here, the complement of A relative to B is this, the set of all X such that X is an element of B and X is not an element of A. And as I mentioned, that this notation is not read B minus A. What that minus sign means it's an operation on numbers, and set difference is an operation on sets. So the complement of A relative to B is the same as saying the intersection of B and the complement of event A. And it looks like this in the Venn diagram. That's going to be the set of all elements in B and not in A. So you'll be considering for that, according to the Venn diagram, this shaded part right here, where the intersection is not included and A is not included. All right, now let's look at this example. Let's say if A has the elements D, E, F, and B has the elements A, B, C, D, E, F, and C has the elements A, B, and C. Let's say I want to find the complement of B relative to A, and also the complement of A relative to B, the complement of C relative to B, and the complement of B relative to C. Okay. Starting with the complement of B relative to A. Okay. That means all the elements in B, well, that's actually all the elements in A, but not in B. Okay. Now, let's think about this for a moment. Here, if I write this out, A has the elements D, E, F, and then B has the elements A, B, C, D, E, F. That means I'm taking away elements in A that are in B. If I take away the D, and then the E, and then the F, I'm left with nothing, which is going to end up being the empty set. Okay. And then this will be the complement of A relative to B. B has these elements, A, B, C, D, E, F. And A has the elements D, E, F. So if I take away elements in B that are in A, which is in this case D, E, and F, this is what I'm left with from A, just A, B, and C. And then next is the complement of B, the complement of C relative to B, where B has the elements A, B, C, D, E, and F. C has the elements A, B, and C. So if I take away any elements of B that's common to A, because A, B, and C are in set C, I'm left with D, E, and F, which represents the complement of C relative to B. And let's see, the complement of B relative to C. Well, let's see, C has these elements A, B, and C. And then B has the elements A, B, C, D, E, and F. Well, A, B, and C are in set B, so I can take all of those out, and you're going to be left with nothing, which is in this case, the empty set. Okay. All right, next we're going to talk about how to use a Venn diagram as a problem-solving tool. In the previous video for section 2.2, I did introduce you to what a Venn diagram is. Now we're going to be using that to help us solve problems, okay? And this is, Venn diagrams can be used as a problem-solving tool for modeling information. And here's some examples of that on the next page. Let's say M is a set of all students taking mathematics and E is a set of all students taking English. Identify the students described by each region in the figure. Okay, so here is that universal set, and each part is labeled A, B, C, and D. This is region A right here. This contains all students taking mathematics but not English, or we can say the complement of E relative to M. Region B, which is in the middle, as you can see, contains all students taking both mathematics and English, or we could say the intersection of M and E. And then region C, which is the one on the right, contains all students taking English but not mathematics. That would be the complement of M relative to E. And then region D, which is the D located down here in the bottom right-hand corner of that rectangle, it contains all students taking neither mathematics nor English, or the complement of the union of M and E. Or we can say this, the union of the complement of M and the complement of E. Okay. All right, so now we're going to use that Venn diagram to solve problems like this one. Okay. And you might want to pay close attention to this one because one of the writing assignments in this course does require you to complete a Venn diagram and answer questions regarding that Venn diagram. In a survey that investigated the high school backgrounds of 110 college freshmen, the following information was gathered. 25 took physics, 45 took biology, 48 took mathematics, 10 took physics and mathematics, 8 took biology and mathematics, 6 took physics and biology, 5 took all 3 subjects. And you want to create a Venn diagram to answer these questions, parts A through C. Part A is how many students took biology, but neither mathematics nor physics. Part B, how many took physics, biology, or mathematics. Part C, how many did not take any of the 3 subjects. Okay, so I'm going to go ahead and draw the universal set for the Venn diagram, which is a rectangle. Now we're dealing with 3 subjects: physics, biology, and mathematics. So here's what I'm going to do here. I'm going to let this circle represent physics. I'm going to label this as P. And then biology will be this circle. And I'm going to do 3 interlocking circles. So I'm going to let B be the biology. And mathematics would be the 3rd interlocking circle, intersecting circle. Let that be M. Now I'm going to use a technique of working backwards. Okay, I'm going to be working backwards to fill in the numbers here. Okay, so here I'm going to start with the fact that 5 took all 3 subjects. So now physics, biology, and mathematics, the intersection of all 3 will be this space right here that you see here. This is where I'll put the number 5 here. I wish I'd drawn this bigger, but that has the number 5. Okay. Okay, that 5 goes into that circle right there. The circle where those 3, the space where the 3 circles intersect: physics, biology, and mathematics. All right, next it says here, 6 took physics and biology. Okay, here's physics and here's biology. If I find the intersection, it's going to be this right here. Now, I've already got 5 that took all 3. And if it says 6 took physics and biology, that means I need to subtract 5 from the 6. That will give me 1. So that 1 goes here, because here, this whole intersection represents a total of 6. And I've already got 5 here. So that means that this space right here has to be 1. And then 8 took biology and mathematics. Well, biology is here, mathematics is here. This is the intersection of biology and mathematics that I'm outlining here. That has a total up to 6. Well, 5 took biology and mathematics, so that means 5 from 6 will be 1. And that 1 goes there. Next is 8 took biology and mathematics. I'm sorry, 6 took physics and biology. Oh, I got that right there. I'm sorry. Now, 10 took physics and mathematics. Physics and mathematics. That's this intersection right here. That must total to 10. This part right here, it represents the 5. So if I subtract 5 from 10, I would get 5. So that 5 will go here. And now 48 took mathematics. Here's mathematics, the whole circle. That totals to 48. I got 5, another 5, and a 1. So if 48 took mathematics, that means 48 minus 5 minus 5 minus 1. Well, that would be 43. 43 minus 5 would be 38. 38 minus 1 would be 37. So that means that 37 took mathematics. Okay. Okay. All right, next is 45 took biology. So here's biology, this whole circle right here. If 45 took biology, that means I got a 1 and a 5 and a 1. So I need to subtract 1, subtract 5, and subtract another 1. This will be 44, 39, 38. So that means 38 took biology. That 38 goes there. And then 25 took physics. Here's physics right here, this circle. I got a 5 and a 5 and a 1. So 25 minus 5 minus another 5 minus 1. This will be 20, then 15, and then 14. So that means that 14 took physics. Okay. I think I made a mistake right here. Okay. Because 8 took biology and mathematics. That was a 5. So this should be 5 from 8, which would give me 3. Okay. So this should be a 3 right here. And that's going to pretty much change everything here. Okay. 10 took physics and mathematics. Well, if that's 5, that has to be 5. 48 took mathematics. So this will be 5. 48 minus 5 minus 5 minus 3. So this should be 3 right here. That's going to change that 38 to 37 to something else. 13 minus 48 would be 35. So that means 35 took mathematics. And then 45 took biology. So this will be 45 minus 1 minus 5 minus 3. This will be 36. Then 25 took physics. 5, 5, and 1, that's 11. From 25 will be 14. So that's correct. Okay. So here I had to double check my answers here. You want to make sure that you're doing the right thing, subtracting correctly. All right, so now let's use this Venn diagram to answer the following questions here. How many students took biology but neither physics nor mathematics? Okay. Took biology only is another way of saying that. So here in this case, based on this Venn diagram, 36 took biology but neither physics or mathematics. That's what that means. How many took physics, biology, or mathematics? Well, here's what I need to do. I need to add up every single number in each of those 7 regions. So that means I need to add 14 plus the 1 plus the 36, and then 5 plus 5 plus 3, and then plus 35. So if I was to do the math here, let's see, 14 and 36, that's going to be 50 plus 1, that's 55, 51, 56, 61, 64 plus 35 would be 99. So that means that 99 took physics, biology, or mathematics. And then how many did not take any of the 3 subjects? Well, there were 110 college freshmen. So I subtract that 99 from 110. That would give me 11. And that 11 would go right here. Okay, so that's how we create a Venn diagram and use that Venn diagram to answer those questions. Okay. All right, let's take a look at another example that deals with creating a Venn diagram and answering questions. Take a look at homework example number 1. Of the 8th graders at the Paxton School, 8 played basketball, 9 played volleyball, 10 played soccer, 1 played basketball and soccer only, 2 played volleyball and soccer only, 1 played baseball and volleyball only, and 2 played volleyball, basketball, and soccer. How many played one or more of the 3 sports? Okay, so here we're going to create a Venn diagram. And then let's do 3 interlocking intersecting circles. This first one would be for basketball. The second one would be for volleyball. Represented by V. And the third would be for just soccer. Okay. So we just fill in these numbers here. Working backwards, it does say here that 2 played volleyball, basketball, and soccer. The intersection of those 3 sports will be this space right here. So I'm going to put a 2 there. Now pay close attention here. 1 played basketball and volleyball only. Okay, so here in this case, that key word that they give you is only. So that means we don't need to subtract in this case. So basketball and volleyball only, that's this and this intersects to this right here only. So we're going to put a 1 there. And then going backwards, 2 played volleyball and soccer only. Volleyball and soccer would represent this for only. That means only 2 played volleyball and soccer. And then 1 played basketball and soccer only. Basketball and soccer would be this space right here. Okay. And then, let's see, 10 played soccer. Now in this case, it didn't say only. Just 10 played soccer. That's this whole circle right here. So I got a 1 and a 2 and a 2. So I have to do 10 minus 1 minus 2 minus 2. This will be 9, 7, and then 5. So 5 only played soccer. 9 played volleyball. That's this whole circle, represents 9. So let me just say here, S is this, and B is going to be this right here. I have to subtract 1, 2, and 2 from the 9. 9 minus 1, minus 2, minus 2. Well, 9 minus 1 is 8, and then 6, and then 4. So 4 only played volleyball. And then for basketball, which is B, 8 played basketball. So that would be 8 minus these numbers here, the 1, 2, and the 1. That'd be 7, 5, 4. And that's your Venn diagram. Now, the question that they ask is how many played one or more of the 3 sports? How many played one or more of the 3 sports? And in this case here, we need to add these numbers together that are in those regions. So it'd be 4 plus 1 plus 4 plus 1 plus 2 plus 2 plus 5. Let's see, add these together. This will be 5, 9, 10, 12, 14, 19. So to answer that question, 19 8th graders played one or more of the 3 sports mentioned. Okay. So here the key word there was only. That was here and here and here. So that means we did not need to subtract. But for these, they didn't have the word only. So you had to subtract. Okay, here's another homework example. In a fraternity with 33 members, 18 take mathematics, 5 take both mathematics and physics, and 8 take neither mathematics nor physics. How many take physics but not mathematics? Okay, so here we can draw a Venn diagram to see what's going on here. So we're only dealing with mathematics and physics, so I'll let the green be mathematics this time, the green circle be mathematics, and the P be physics, the circle. All right, in this case here, we got 33 members in a fraternity. 18 take mathematics, but let's start with this one. 5 take both mathematics and physics. All right, that's the intersection of math and physics here. That intersection is this region right here, so the 5 goes there. Now 18 take mathematics, that's the whole circle. So for mathematics, that's going to be 18 minus the 5 that's in the center. That would give us 13. And also we're told that 8 take neither mathematics nor physics. So the 8 will have to go somewhere on the outside of those 2 circles. And there are 33 members in the fraternity. So we're going to subtract these numbers that we already know. So I'm going to do 33 minus 13 minus 5 minus 8. 33 minus 13 will be 20. 20 minus 5 is 15. 15 minus 8 is 7. So in this case here, 7 took physics, but not mathematics. 7 took physics, but not mathematics. Okay. All right, here's another homework example dealing with Venn diagrams, and that's this. In a survey of 1,140 investors, it was determined that 730 invested in stocks, 595 in bonds, and 340 in both stocks and bonds. So we'll have the Venn diagram, fill in the numbers, and then answer the three questions. Part A, how many invested in only stocks? How many invested in stocks or bonds? And then part C, how many did not invest in either stocks or bonds? All right, so here we're given that, in this case here, 340 investors invested in both stocks and bonds. That's the intersection here, which is actually region number 2. So that 340 would go here. And then 595 invested in bonds. So here for bonds, that's going to be the 595 minus the 340. Because this right here represents the bonds. And we already got 340. So if we subtract 340 from 595, you will get 255. Yeah. So the 255 goes here. And then 730 invested stocks. Well, A represents the stocks. So that goes here. So if there's 730, subtract that from 340, you'll get 390. So that 390 goes here. All right, so now we can use that to answer the following questions. How many invested in only stocks? Well, that's this number right here, stocks only, 390. And then how many invested in stocks or bonds? Stocks or bonds. That's this region and this region. 390 plus 255. That would be 645. So 645 invested in stocks or bonds. And how many did not invest in either stocks or bonds? Well, there were 1,140 investors. We're going to subtract 390, 340, and 255 from 1,140. Okay. Probably would be best if I said it like this, 390 plus 340 plus 255. Take that sum and subtract 1,140 from it. Let's see, 390 and 340 is 730. 730 and 255 would be 985. And then subtract 985 from 1,140, you'll end up with 135. Correction, 155. Okay, 155. I want you to know that I'm doing all of this without a calculator. So in this case, the answer part C, 155 investors did not invest in either stocks or bonds. All right, so that's how we use a Venn diagram to answer these types of questions. All right. So here they don't give you a Venn diagram. They want you to create one and answer the problem's question. A poll of 150 people determined that 123 had subscriptions to the hard copy of a newspaper, 35 had hard copy and online subscriptions, and 13 had neither. How many had only online subscriptions? Okay, so Let's draw a Venn diagram to represent this situation. So this circle here will represent hard copy, which is H. And the other one will be the online subscription. That's O. So let's take a look at what we have here. 13 had neither, so that 13 would go on the outside of those two circles. 35 had hard copy and online subscriptions. That's the intersection of hard copy and online, this intersection, 35. And 123 had subscriptions to hard copy, the hard copy of the newspaper. That's this whole thing right here. So we know that the intersection is 35. If I subtract 35 from 123, this will give me 88. And then how many had only online subscriptions? So we're looking for this region right here. Well, let's do this. That's 123 minus 88 minus 35. I'm gonna put the 35 first and then minus 88 because I know what 123 minus 35 was. Actually, I'm doing this wrong. The total is 150. Okay, 150 were polled. So 150 minus 88 minus 35 minus 13. 150 minus 188, 150 minus 88 would be 62. Then 62 minus 35 would be 27. And then 27 minus 13 would be 14. So that means that 14 had only online subscriptions. Okay. Here's another homework example dealing with Venn diagrams. Now here they give you the regions and they tell you the number in each of those 8 regions, okay? So in this case here, we just fill this in with the appropriate numbers based on this information. The number of elements in A is 38, and in B is 40, and in C is 25. The number in the intersection of A and B, that's 16. The number of elements in the intersection of B and C is 14. And then for the intersection of A and C, it's 11. Then the intersection of all 3 would be 4. And the number in the universal set is 78. All right, let's start with this one. The number of elements in the intersection of all 3, A, B, and C. That's going to represent region number 5, which is actually 4. So region 5 has 4 elements. Now for the intersection of A and C, that's 11. Here's A, here's C. That represents region 7 right here. That total has to be 4. 4, I think. Yeah, it has to be 4. Okay. Let me retract that. That's 11. I'm sorry. A and C. Here's A, here's C. That so has to be 11. We got the 4, so 11 minus 4 would be 7. So region 7 has 7 elements. And then for A, the intersection of A and C, that's totals 11, which I already did. Now for B and C, the intersection of B and C is 14. Here's B and here's C. That's this whole thing, that totals 14. We got 4, so if I subtract a 4 from that 14, that will be 10. This is for region 8, which has 10 elements. All right, and now for the intersection of A and B, here's A and here's B. That's this intersection must total 16. We got the 4, so 4 from 16 will be 12. So region 6 has to be 12. And now for the number of elements in C, all of this represents C. That's totals 25. We got 7 and 4, that's 11, plus 10 is 21. 21 from 25 would be 4. So this represents region 3. And then the number of elements in B is 40. That's this circle right here. We got 12 and 4, that's 16, plus 10 is 26. If I subtract 26 from 40, that would be 14. That represents region 4. And then finally, the number of elements in A, that's going to be 38. That's the total. Here, I got 12 and 4, that's 16, plus 7 is 23. 23 from 38 would be 15. That's region 2. All right, and now the number in the universal set is 78. So that means I need to add all of these numbers that I have here in those regions and subtract that from 78. All right, so if I do 15 and 12, that's 26, plus 14, that's 40, plus 10, that's 50, plus 4, 54, plus 7, 61, and 4, that's 65. Subtract 65 from 78. You'll end up with 13. Correction. Oh, I see. Well, I messed up it. That's 27. 27. 27 and 14 will be 41. 41 and 10 will be 51. 51 and 4 will be 55. 55 and 7 will be 62. 62 and 4 will be 66. So if I subtract 66 from 78, 66 from 78 would be 12. And that 12 is going to be region 1. Okay. Okay. So here, I was just filling these in to come up with the answers for those 8 regions in that Venn diagram. Okay. All right, next we'll look at Cartesian products. All right. One way to produce a set from 2 sets is by forming pairs of elements of one set with the elements of another set in a specific way. Suppose a person has 3 pairs of pants, where P will be the elements blue, green, and white, and 2 shirts, where S has the elements blue and red. According to the fundamental counting principle, there are 3 times 2 or 6 possible ways to pair an element from set P with an element from set S, forming a set of ordered pairs. And here's that figure that shows you the actual pairing of the colors of shirt to the color of pants. Because the first element in each pair represents pants, and the second component in each pair represents shirts, the order in which the components are written is important. Okay. Order is going to be very important, as you can see here. Okay. Now, next, I'm going to define equality of ordered pairs. And in this case here, the equality of ordered pairs is this: x comma y is equal to m comma n if and only if the first components are equal and the second components are equal. And that should be if and only if. And a set consisting of ordered pairs is an example of a Cartesian product. And in this case, for any sets A and B, the Cartesian product of A and B is written like this. And that is the set of all ordered pairs such that the first component of each ordered pair is an element of A, and the second component of each pair is an element of B. So in set building notation, and this is actually A cross B, or the Cartesian product of A and B. That's going to be the set of all ordered pairs X and Y, such that X is an element in A and Y is an element in B. And of course, we read that as A cross B and not A times B, because times is when you're taking the product of two numbers. A cross B is when you're dealing with the ordered pairs. So here's some examples of this, of dealing with the Cartesian product. Let's say A has the elements A, B, and C, and B has the elements 1, 2, and 3. And I want to find the Cartesian product of A and B, the Cartesian product of B and A, and the Cartesian product of A and itself. Okay. So the cross product of A and B, or A cross B, I'm writing A as the elements A, comma, B, comma, C, and B, 1, comma, 2, comma, 3. So to find that Cartesian product, I take each element in the first set, pair it with each and every element in the second as ordered pairs. So here A would be paired with 1. So I have A comma 1. A would be paired with 2, A comma 2. And then A is paired with 3, A comma 3. And then the second element would be paired with each and every element of the second. The second of the first set would be paired with each and every element of the second. So now B would be paired with 1, B would be paired with 2, B would be paired with 3. And then finally, C will be paired with each and every element of the second. Okay, so C will be paired with 1, C is paired with 2, and finally C is paired with 3. Okay. Now part B is the cross product of B and A. Well, B has 1, 2, and 3, and A has A, B, and C. So in this case here, the 1 would be paired with each and every element of the second. So 1 would be paired with A, and then 1 will be paired with B, 1 is paired with C. Then 2 would be paired with each and every element. So here, 2 is paired with A, 2 is paired with B, 2 is paired with C. And then finally, 3 will be paired with each and every element of the second. So 3 is paired with A, 3 is paired with B, and 3 is paired with C. And part C, A cross A. Well, of course, it has the elements A, B, C. Now copy the elements in A over. So in this case here, A is paired with every element in the second. So A is paired with A is paired with B, and A is paired with C. And then B will be paired with each and every element. So B is paired with A, B is paired with itself, B is paired with C. And then C will be paired with each and every element as well. So C is paired with A, C is paired with B, C is paired with itself. Okay. So that's how we write the Cartesian product of A and B, and then B and A, and with A in itself. Now, it is possible to form a Cartesian product involving the null or empty set. So suppose that A has the elements 1 and 2. Because there are no elements in the empty set, there are no ordered pairs for X and Y, with X being an element of A and Y being an element of the empty set. So the cross product of A and the empty set is the empty set. And also the cross product of the empty set and A would be the empty set for all sets A. All right, now let's take a look at this homework example. Let's let A have the elements M and P, and B has the elements A and B. So here we're going to use this information to complete parts A and B. Part A is to find A cross B. Part B is finding B cross A. And then in part C, we want to answer this important question: does A cross B equal B cross A? So that's going to be very important here. So let's start with part A. That's A cross B. A has the elements M and P. And then B has the elements A, B, and C. So that means the first element in the first set would be paired with each and every element of the second set. The second element in the first set would be paired with each and every element of the second. So M is paired with A. And then M is paired with B. M is paired with C. And then next, P is paired with A. P is paired with B. And P is paired with C. And now part B, the cross product of B and A. So now you got A, B, C for your B, and then MP for set A. So this time A would be paired with M, and A would be paired with P. And now B would be paired with M, and then B would be paired with P. And then finally, C will be paired with M, and then C will be paired with P. Okay, so that's the cross product of B and A. Now part C, does A cross B equal to B cross M? And if you look at this, the answer there will be no. And the reason for that would be that the corresponding pairs in each product have different, well, the components of the corresponding pairs in each product are reversed. Okay, here, when you did A cross B, you had MA, and then for B cross A, it was AM. So those pairs reversed. So that's homework example number 6. All right, and finally, homework example number 7 is this. For each of the following, the Cartesian product C and D is given by the sets listed. Find C and D. So we have their Cartesian products. We want to find out what set C started off and what set D started off as. All right, set C was pairing the first element with the of set C with every other element, because in D, the elements in D were the second. So we only look at the first elements, or the first coordinates, I should say, first components here. That's going to tell me what C is. Here I just got S all the way through. So C had only set S. Whereas D, that would be your second components here. B, C, D, and E. And now for part D, the cross product of C and D came out to this. Well, C will be coming from your first order pair, or the first components in each order pair, which you can see that I'm highlighting here. I only have a 4 and a 1. So for C, it was 4 and 1. C had the elements 4 and 1. D will be your second components, 1, 2, 3, and again, 1, 2, 3. So D had these elements, 1, 2, and 3. And then finally, C C cross D ended like this. So for C, we look at the first component of each of those ordered pairs. We only had the 4 and the 1. And D, we'll look at the second components of 1 and a 4. Or you can say 4 and 1 if you like. Okay, so this is just working backwards to find out what what's the set for C and the set for D. Okay, all right, so that does conclude this video, section 2-3, dealing with the other set operations and their properties. Do feel free to email me if you have any questions or concerns about what's presented in this video and whatever is presented in the homework in my math lab. Okay, take care.